Everyone says Android runs on Linux. But have you ever wondered why you can't just apt-get upgrade the kernel on your phone? Here is what actually happens under the hood. The highlighted text says Android is built on the Linux kernel, but it's a massive misconception that it's a standard Linux distribution. The kernel on your phone has been fundamentally altered for the unique world of mobile hardware. This distinction is the source of nearly all platform-level complexity you'll encounter. So if it's not mainline Linux from kernel.org, what is it? Google doesn't use that kernel directly. Instead, as you see highlighted, we maintain our own fork. This fork is called the Android Common Kernel, or ACK. Think of it as a parallel universe to mainline Linux. It starts from a specific long-term support release, but then we graft on a whole new set of Android-specific DNA. You can find its source tree inside AOSP under the common/ directory. But why go through all the trouble of maintaining a massive kernel fork? The first reason, as highlighted here, is aggressive power management. A server in our data centers is designed to be awake and processing requests 100% of the time. Your phone, on the other hand, is designed to be asleep over 99% of the time to survive a full day. This requires a completely different philosophy of power management, baked deep into the kernel's scheduler and drivers. Beyond power, the other big reason was the wild west of hardware drivers. Most people trip over this because they assume drivers are standardized. They are not. As this line shows, silicon vendors like Qualcomm and MediaTek wrote their own proprietary drivers for their chips. These were complex, not written to mainline standards, and were never accepted upstream, so we had no choice but to bolt them onto our forked kernel.
To make Android actually work, we had to invent new kernel subsystems. And the most important one is right here, Binder. Every single time your app talks to a system service, from showing a notification to getting your location, it's a Binder transaction. It's an incredibly optimized IPC mechanism that allows sandboxed apps to securely communicate with the privileged system server process. I personally refactored parts of this in Android 11. It is the absolute central nervous system of the entire OS. Now, how do you keep the device asleep while still doing useful work, like playing music? That's the job of Wakelocks, a concept you see highlighted here. When your music app service acquires a wake lock, it's telling the kernel, hey, I know you want to go into deep sleep, but please keep the CPU partially awake until I release this lock. It's a powerful tool, but historically the number one cause of battery drain when abused by apps. What happens when you run out of physical RAM on a device with no swap file? On a desktop, it thrashes. On Android, the low memory killer, or LMK, takes over. This is a brutal but necessary kernel demon that monitors memory pressure. When it gets too high, it looks at the score edge of every running process and starts killing background apps, starting with the least important, to reclaim memory for the foreground app. It's why your game doesn't crash when a high priority notification arrives. The last of the big three patches was ASHMEM, or Anonymous Shared Memory. This is a mechanism that allows different processes to share large chunks of data without copying it, which is critical for things like graphics buffers. Over the years, many of these core Android ideas, especially Binder, were so good that they were cleaned up and actually merged back into the mainline Linux kernel. But that didn't solve the bigger problem with drivers.
You can actually see all the custom kernel modules running on your own device right now. If you connect your phone and run the command you see on screen, adb shell lsmod, the system will print a list of all the dynamically loaded kernel modules. You'll see drivers for your Wi-Fi chip, your display panel, and all the other hardware that makes your specific device unique. This list is a direct fingerprint of the fragmentation we are about to discuss. This whole approach created a nightmare of fragmentation. The trick that took me years to fully grasp is that the kernel on your phone is at least 4 layers of patches deep. It starts with mainline Linux, then Google adds ACK patches, then Qualcomm adds chip patches, then Samsung adds device patches. The result, as highlighted here, is what we called a Frankenstein kernel. impossible to update, and riddled with security holes that could never be patched. How do you fix a problem that fundamental? You draw a hard line in the sand. Starting with Android 11, Google introduced the solution you see highlighted, the Generic Kernel Image or GKI. The philosophy is identical to Project Rebel, which separated the Android framework from vendor HALs. GKI aims to do the exact same thing but for the kernel itself. This was one of the biggest architectural changes in Android's second decade. Here is the core idea of how GKI works. Vendor-specific code is forbidden from the core kernel. Instead, as you see in this line, vendors must now compile all their proprietary drivers as separate loadable kernel modules or .ko files. This means the main kernel binary, Vim Linux, is generic and identical across all devices, while all the device-specific hardware support is isolated into modules that can be loaded at runtime.
But how can a module compiled today work with a kernel I build next year? That's the magic, highlighted right here. Google now guarantees a Stable Kernel Module Interface, the KMI. We promise that the function signatures and data structures that these modules rely on will not change for a given kernel version. This allows us to ship a single pre-compiled generic kernel in a boot.img that can boot on any GKI compliant device and just load the necessary vendor modules. So why does this matter so much? With GKI, we can finally update the core Linux kernel on your phone directly without the silicon vendor. As you can see highlighted, this means we can push critical kernel security patches through Google Play system updates or standard OTAs. This dramatically improves device security, extends the useful lifespan of a device by years, and makes life for custom ROM developers infinitely easier. Finally, look at the code shown here. This is a tiny piece of a makefile for building a vendor module. That objm line tells the build system to compile myvendordriver.c as a loadable module, a KO file, instead of building it into the main kernel. The rest of the command points to the GKI kernel headers to ensure it's built against that stable KMI. This simple text file is the enforcement mechanism for the entire GKI architecture.
Enjoyed the video? Hit like and subscribe for your regular dose of AOSP customization. Thanks for watching. See you in the next one.